Welcome back, Physics 30. So we talked about the principle of equivalence, which states that an object accelerating upwards is equal and opposite to gravity pulling downwards, and there's no experiment we can do to tell the difference. And we looked at the flashlight beam. If it's shining straight across and if the object is accelerating upwards, the beam goes straight across, but according to us in an elevator, it looks like it's bending down because by the time the light has moved across, the elevator has moved up, so the beam hits a spot slightly less. So if that's true with an accelerating body, it must be true as if gravity was operating in the opposite direction. So that light is affected by gravity is an important prediction of Einstein's general theory of relativity, and it can be tested. The amount of light beam would be deflected from a straight line path must be even small when passing a massive object. And of course, to get a large gravity, you need a larger and larger, more massive object. So for example, Jupiter compared to Earth exerts a lot more gravity compared to Earth because it's a more massive object. So if we look over here, so for example, light near Earth's surface traveling at 1 kilometer per hour is predicted to drop only by about 10 to the negative 10 meters, which is equal to the diameter of a small atom and not detectable. But the most massive object near us is the Sun, and it was calculated that light from a distant star would be deflected 1.75 of arc. Tiny but still detectable as it passed by the Sun. However, such a measurement could only be made during an eclipse so that we wouldn't have starlight or sunlight obscuring our view. So here, if we see light from a normal star, of course it follows a straight line. But if we have a star, if you see slightly on this side of the Sun, and if our moon happens to be here, starlight, instead of going straight, could get curved towards us. And of course, if we extrapolate this line backwards, it appears that the light, we know that light travels in straight lines, it appears that that star is actually here, but when in fact it is here. So the weird thing there, acceleration causes that bending of a light beam. So equivalently we can say gravity must exert a pull on light, and sure enough, it does. Another example here is looking at a quasar, a body that emits a lot of light, and looking at a galaxy. If we're over here, of course we could see a galaxy. In a telescope it would show up as a bright light. And interestingly enough, of course, a galaxy would be massive because it contains a lot of planets, etc., a lot of solar systems. So light here, instead of moving out this way, would get curved, being pulled by gravity, and then simply continue on in a straight line. And if we extrapolate those lines backwards, we would see a false image here, a false image here, and a false image in a variety of spaces. So the middle light here would be the galaxy, and these false images around would be the false images of this quasar, or a body that's emitting a lot of light. So we could see examples of that. Also here, an opportune eclipse occurred in 1919, and scientists journeyed to the South Atlantic to observe it. Their photos of stars just behind the Sun revealed shifts in accordance to Einstein's prediction. Another example of a gravitational deflection is gravitational lensing, as described up here, like I mentioned. So we can see that there's a deflection around a large body, or not a deflection, but an attraction, curving it out of its straight line path, making a new straight line path, and extending those lines backwards. And knowing that light travels in straight lines, it appears that the real bodies are in this area, but in reality that light was curved. The mathematician Fermat showed in 1600 that the optical phenomena, including reflection, refraction, and effects of lenses, can be derived from the simple principle. Put a star beside this. Light traveling between 2 points follows the shortest distance path in the shortest path in space. Thus, if gravity can curve light, as we see in these examples from back here, because we could also look at it as acceleration in one direction, gravity in the other. So if an object can do that, if gravity can curve light, then gravity must also be able to curve space itself. That is, space itself can be curved, and it is a gravitational mass that causes that curvature. Indeed, the curvature of space, or rather four-dimensional space-time, is a basic aspect of Einstein's general theory of relativity. And of course, what do we mean by curved space? So in the next page, we kind of look at, okay, what is meant by curved space? And it's kind of difficult to understand, so hopefully we can go through this at a pace, and we'll kind of get an idea of what do we mean by curved space. So to understand, recall our normal method of viewing the world is via Euclidean plane geometry. In that geometry, there are many axioms and theorems we take for granted, such as if you add up the angles in any triangle, it works out to be 180. So that is true for two-dimensional space. So a flat plane, a piece of paper, you can draw a triangle, measure all the angles, they add up to be 180. So non-Euclidean geometry, such as involves curved space, has been also imagined by mathematicians. It's hard enough to imagine three-dimensional curved space, much less curved space in 4 dimensions. So we try to understand that. So looking at this example, the two-dimensional surface of a sphere, it's clearly curved, at least to us who view it from the outside, from our three-dimensional world. But how about hypothetical two-dimensional creatures? How if you were traveling on the Earth like we do, to us the Earth appears flat, just like a piece of paper. If in a small area we draw a triangle, add up the angles, we get 180. But if we take a larger distance and draw a triangle, so if we're along the equator, and of course from this view it looks curved, but from our view it's just a straight line. Then from one point go to the North Pole, it appears to be a straight line. From over here, from the equator, go and draw a straight line to the North Pole, and if you notice here, first of all, before we look at that, the shortest distance between points on a curved area is called a geodesic. On a sphere, a geodesic is an arc of a great circle, such as the equator. Now here we can see it's an arc, but if we were on the Earth drawing that, we would see it as a straight line. So if we draw a triangle, you can see here, this angle would turn out to be 90, 90, and 90. Okay, so if we take a look here, this would be a geodesic, so it was the shortest point between two places on a curved body. So of course we can see that's a curve, but according to us on that planet, it just looks like a straight line. So yes, we see that the angles do not add up to be 180, they add up to be 270. So this is clearly not a Euclidean space, it's not a two-dimensional plane, a flat piece of paper. Note, however, that if the triangle is, we've made a smaller one in comparison to the radius of the sphere, the angles do add up. Okay, so if we did draw a smaller triangle, everything works how it should on a flat plane. But the further the distance is, you can see that it turns out that we must not be working on a flat space. Okay? Another way of determining if we're on a curved space or not, so looking at triangles that don't have to be 180, we can look at looking at circumferences or distances around or making a circle and figuring that out. So of course, you know that circumference is equal to 2 pi times the radius. So if we draw a circle, so if we draw a circle up here, a small enough circle, make a dot, extend out a radius, draw a circle, c equals 2 pi r. Okay, but the larger that circle is, of course, that curved space is being taken into account. We measure this as the radius, and here's our circle. And you can see if I was to take a piece of paper and insert it through the Earth, the actual center of the circle is here. But to us, our perception is that this is radius and not this. And you can see that A, the real radius, is a heck of a lot smaller than this curved radius. So of course what ends up happening here is that on this spherical surface, the actual circumference is less than the circumference I would figure out if I figured out 2 pi r here. If I took 2 times pi times this radius, actually measure out the circumference, they don't equal. So that tells us that we must be, and of course with this, when this happens, is that their circumference is less than when I just simply take pi times r times 2. And that would tell us that we're in an area that has positive curvature, so like a globe like this. If you have a saddle-like structure like this, so again, if we make a circle near where the dot is, it should work out, but the larger that circle gets, it wraps around this way and around on the other side. We get the circumference being bigger than it should be when we use our pi. Alright, we'll take a look at that some more on the next video.